Good morning, Mayfield students. Here's our next calculus lesson. It is lesson 5, according to the old schedule, of Unit 3, the Cartesian equation of a plane. So this is our second post-extended break lesson. We will be doing one more. It'll be out today as well. The only lesson we're actually going to be doing from Unit 4, which will be the intersection of a line and a plane. So before we get started, I just wanted to go back to the note that I made uh, at the beginning of last lesson to summarize what we've done with the equation of lines so far. So I realized I made a little mistake here, so I have to correct that. So the equation of the line in R2, basically since it's R2, you can tell from the equations because it just has X and Y components in any of the equations. Um, you can tell it's not a plane. Well, first of all, it has to, in R2, there are no planes. Well, there is one plane, which is the whole XY plane, but we don't consider planes in R2. So when we extend from R2 to R3, all the equations basically get extended. We add a second, we add a third component, the Z component, in each of the direction vectors, the position vectors. You can see that there's three parametric equations, three sides to the symmetric equations. Okay, now this was the mistake I made. There are no Cartesian equations for a line in R3. That equation I gave you inadvertently is the Cartesian equation of a plane in R3. So that's what we're going to be talking about today. So I apologize for that. If you want to just, if you made notes on that, please take away the Cartesian equation of a line in R3. We won't be, those don't exist in this course. Okay, so if we extend, I'll just kind of summarize the important parts of today's lesson, and then we'll get into the lesson. Now, as soon as we start talking about planes, like we did in the last the last lesson, what happened if I put this side by side with a line in R3, you can see that we've gone from vector equation has a position vector and one direction vector, whereas the planes, we add that second direction vector because you need two direction vectors to define a plane. So we've got this second direction vector B with a new scalar t. So that's what the vector equation looks like. If we expand it in component form like this, each one of these vectors has three components, x, y, and z component. And then if we expand it, we can get this equation, which is another version of the vector equation. This is a good form because it gives us the parametric equations directly. You can just read x is equal to this, y is equal to this, z is equal to this. Those are the parametric equations. And like we said last lesson, the symmetric equations, there are none, simply because we have two scalars now. So we can't really just isolate for the single scalar because there's two of them. And here's the Cartesian equation. This you can tell it's an R3 because it's got an x, y, z. Now none of these are vectors. These are just scalars and variables here. Okay, so you can tell it's R3 because it's got x, y, and z. And anytime you see a equation written like this, you can tell it's always going to be a plane, and a plane in R3 because that's the only planes we're going to be talking about. Now, we'll get into this in a few minutes, but the A, B, C, and we use capital letters for this, capital A, capital B, capital C, that forms a vector that's actually a normal vector to this plane. Okay, now we can't get we can't get a direction vector or two direction vectors directly from this. Today's lesson we're going to show how we can be given any Cartesian equation and convert it into vector equations or parametric equations. Okay, so let's look at the lesson now. So basically we got the same definitions up here. We have the plane, a flat two-dimensional surface that extends infinitely far. Now in the drawings, we just draw a parallelogram because otherwise, if it has no edges, we can't really see it. So we just kind of draw a part of the plane, which we draw as a parallelogram. So in your homework questions, in the pictures below, you'll see planes are parallelograms in R3. And anytime we talk about a plane, we use the symbol pi. Okay, and this is what I just talked about. A normal vector is it's a vector that's perpendicular from a plane. So there's obviously more than one. There's actually an infinite number of normals for each plane, but we can get this vector, this normal vector, directly from the Cartesian equation. And we could also say ABC is a point on that vector. Okay, the Cartesian equation, this is what we just talked about. Here's its form. Here's the fact that the ABC are components of the normal vector. And if we look at the drawing down here, let me just zoom in. Okay, so if we have this plane, this blue parallelogram in R3, that's the plane in question here. You can see the label pi up there. Okay, you can see the X, Y, Z axes here to try to show that it's in R3. So if that's our plane, this vector, this normal n with components ABC is a vector that's perpendicular to the plane. So that's sort of how you can relate to that visually, or geometrically. Okay, here's another representation, another plane in blue. This time we have 2 points on the plane, P naught and P. If we draw a line between the 2 points, that would be considered a direction vector on the plane, and we can get a normal to the plane, which goes perpendicularly through the plane in that. Okay, so that's the visual representation of what we're going to be doing. If we go back to the key concepts, let me zoom out again. Okay. Again, here we have a definition of a plane in R3. The normal is ABC. And if we further extend that normal vector, if we had 2 vectors A and B that were two non-collinear direction vectors on the plane, we can get a normal by just doing the cross product of the 2 to come up with a normal. So we did this last unit. Okay. Now, this should be obvious, but basically if you have 2 planes and the normals are n1 and n2, those 2 planes will be parallel, meaning they'll never touch, if and only if one normal is a scalar multiple of the other. Okay, and if you had 2 planes with those 2 normals, they would be perpendicular if you did a cross product of the 2 and got 0. And this is the one we haven't done yet. You can figure out the angle between 2 planes by this formula here. This looks a lot like what we did between the angle between 2 lines, except we didn't do normals. We did direction vectors. So again, it's the angle is the cos inverse of the dot product of the normals divided by the multiplication of their magnitudes. Okay, so that's how you get the angle. Now, there's actually how you measure the angle between two planes, it's relative. So there's actually two angles. There'll be one that you get from here, and then the other one will be 180 minus whatever this angle is. Okay, we came across that issue with lines as well. Okay, so let's do some typical questions around Cartesian equations of planes. Okay, so we're going to represent a plane by its Cartesian equation. In other words, here's some information. What's the plane's Cartesian equation? So in this case, we have a point A, coordinates 3, 4, 1. Notice I've got the round brackets. That tells you it's a point. And that the plane has a normal -2, 3, -1. Determine the Cartesian equation of the plane. Okay, now there's two, I'm going to show you two methods of doing this. I think most of you would probably prefer the second, but I'll show you both anyway. So here's method A. Okay, now what I'm going to do, I'm going to call this also refer to A as P naught, but I'm also going to have a generic point on the plane, just call it X, Y, Z, point P. Okay, so if I wanted to come up with a direction vector between A and P, or P naught and P, that direction vector, we'll call it AP. We're just subtracting the components. So in this case, it's X minus 3. Sorry, that should just be X minus 3, Y minus 4, so Y minus 4, and Z minus -1, which is Z plus 1. So that's a direction vector on the plane. Now, we've got the normal of the plane, and we've got I'll just call this M, to let you know it's a direction vector. If I do a dot product between M and N, or AP and N, as I've called it, AP dot N, that has to equal 0, okay, because if we do the dot product between the normal and the direction vector, the result always should be 0. So if we do the dot product, so remember, these are the three components of the normal. So if I take the normal and I multiply with the direction vector components for each of X, Y, and Z and add them together, so I've taken -2 times that, plus 3 times Y minus 4, sorry, that should be -1, -1 times Z plus 1, that has to equal 0. So if we simplify this, I'll just skip a step here, but you can see I'm going to have a -2x, I'm going to have a plus 3y, and a minus, that's a minus z, and the numbers here add up to -7. Okay, well that's pretty much a Cartesian equation right there. You can see the values A, B, C, and we actually figured out what the D value would be for this exact plane. Now, usually we don't like to have, and this is true with standard equations of lines as well, don't like to have the A value as negative. We like to have everything as integers, and the A should be positive. So remember, we can always just multiply this whole equation by any real number we want. So in this case, I just want to multiply it by -1 to turn that into +2. So all the signs get flipped. So basically it's the same equation, but this is a little bit more palatable for math people, just because you have a positive value there. Okay, so that's one way of doing it. Here's the way you probably prefer, because we already know that I could get the equation of the plane with this normal just by using this equation. the generic Cartesian equation. I know that that is A, B, and C, so I'll just plug them in. So I get negative 2x plus 3y minus z. And the problem is we don't know what d is. It still has to be a variable. Because there's lots of planes that have this normal, we have to come up with a specific plane which is determined by that value of d. So how do we get that? Well, this should remind you back to your days in grade 9 and 10. We're going to basically plug in this point a. So I'll say substitute a, and so I get negative 2 times 3 plus 3 times 4 minus negative 1, so negative 1 plus d equals 0. Okay, and if we add all this together, we're going to figure out that d is equal to negative 7. So I can now plug this back into the equation we just had, and we get negative 2 plus 3y minus z minus 7 equals 0. And you can see that's exactly the same equation we had here. And again, let's multiply it by negative 1 just to make it more mathematically pleasing. So that turns into a plus 7 equals 0. So either of these two methods is acceptable. Personally, I prefer to do it this way. This is more, a little more work to it, I think, doing the dot product. This is just create an equation, plug something in. So, okay, example 2. Again, we're going to create a Cartesian equation of a plane. This time we're going to do it from 3 points. Okay, so we were doing this last lesson. We weren't creating the Cartesian equation, but we were creating the vector equations. So what we're going to do here is, since we've got 3 points, well, we actually, that tells us 3 position vectors to get to the plane. So we could use any one of these points, turn it into a position vector just by putting the square brackets around. What we need additionally are 2 direction vectors, just like last lesson. So I'm just going to create 2 direction vectors. So it's basically subtracting the coordinates here to get the direction vectors. So if I did, let me see here, if I did BC, so I start with C, so 0 minus negative 1, 1 minus 1, and 1 minus negative 1, 1 plus 1. So that's our first direction vector. This is CB. So I guess it would be BC. Yeah, this would be vector BC, which we're going to call our first direction vector. Our second one, as long as we use 2 different points. So in this case, I'm going to use D and C. So I'm going to call vector DC, I'll call that the second direction vector. So when I'm subtracting, I go in that order. So negative 4, 3 minus 1, and negative 2 minus 1. So there's our 2 direction vectors of that make up this plane, 2 possible direction vectors. So if I do the cross product of the 2 direction vectors, I'm not going to do the work here, I'll just leave that to you, but doing the cross product between these 2, we get this vector here, negative 4, negative 5, 2. Now remember, anytime we do the cross product between any 2 vectors, we get a new vector that's perpendicular to these original 2 direction vectors. So actually what we've just created here is the normal vector of this plane. So that's good, because that means that this is our A, this is our B, this is our C value. Okay, so I can take those values and start creating my Cartesian equation of the plane. So I have negative 4x minus 5y plus 2z. Again, we don't have the d value. We have to actually find that using a point. So what we do, this time we actually have 3 points to choose from. I'm going to pick the easiest one. I'm going to substitute in c. Substitute c. So I get negative 4 times 0 minus 5 times 1 plus 2 times 1 plus d equals 0. And that will tell us that d is equal to 3. And then I'm just going to plug this back in here. So I get negative 4x minus 5y plus 2z plus 3 equals 0. And again, don't like to have that a value as negative. I could have actually switched it up here, but might as well just switch it at the end. So just multiply the whole equation by negative 1, so it flips the signs. And we'll call this pi for the plane, and that's our equation. I guess I should do that up here too. Okay, so that's how we get the Cartesian equation of a plane from 3 points. This is how we get it from, I guess, a normal and a point. Okay, example 3. Okay, so this time we're given the Cartesian equation and they want us to create the vector and parametric equation. So this is definitely a required skill. Here's our Cartesian equation here. Now, what we want to do is try to isolate one of these variables, and you'll see why in a second. So what I'd like to do, pick the best variable to isolate for. So that would be x, because the coefficient is 1. So I can rewrite the Cartesian equation to look like this. So I just basically subtract all 3 of these terms from both sides. I get x equals 2y minus 3z plus 6. Okay, so why did we do that? Well, that's going to help us. We're actually going to come up with 3 points on this plane. So I am going to draw, we did something similar to this last lesson. This table is a little bit smaller. So it's got columns for x, y, and z. These are coordinates. And I'm going to have 3 points here. So this will be first point, second point, third point. Okay, so all I really need to do, I can calculate x if I know values of y and z. So I'm going to just randomly pick 3 different combinations of y and z values. So let's make this as easy as possible. So we could do 0, 0 as one possible point. We could do 1, 0 and 0, 1. Okay, and obviously there's an infinite number of points on this plane, so we can choose any combination of y and z, and there will be a point for that. All we need to do now is calculate what the x value is. So if we plug in, for example, if y and z are 0, for that point the x coordinate would be 6. Okay, and similarly, if y was 1 and z was 0, that would be 2 plus 6, so that's 8. And if y was 0 and z was 1, that'd be negative 3 plus 6, so that would be 3. So these are 3 points on the plane. Okay, so now we do, we got the 3 points. So basically what we do is what we did last lesson. We take these 3 points, we create 2 direction vectors by just subtracting the coordinates. So if I do P1, P2 to get the first direction vector and I subtract, I get 2, 1, 0 as a direction vector. And if I get my second direction vector, maybe I'll go between P2 and P3. So if I subtract P3 from P2, I'm going to get 5, 1, negative 1. So there's two direction vectors. So now it's pretty easy. We've got two direction vectors. We've got our choice of 3 points that we just created from the Cartesian equation. So we can go right to the final answer here. The equation of the plane. Now, like I said, you could pick any 3 of these points as our position vector. I'm going to pick 6, 0, 0. That's our position vectors. And then we have our 2 direction vectors, which come from the ones we just created. So 2, 1, 0 and 5, 1, negative 1. S and T values, it doesn't have to be, we just happen to use S and T as our scalars, just out of habit, just like we use X and Y a lot. It could be any 2 variables. So there's the vector equation. Now the symmetric, sorry, not symmetric, the parametric equations, we could just create those directly by looking at this. So we can say that, well, the X component, that's going to be 6 plus 2S plus 5T. The Y from there would be 0. We don't even have to say it really when we write it. So it's just going to be S plus T. And then the Z value will be, again, 0 here, so we don't have to write it. 0S, so we don't have to write that. And then negative T, so Z is just equal to negative T. So those are the parametric equations, and there's the symmetric equation. Sorry, the vector equation. Okay, so really it comes down, get 3 points on the plane using the Cartesian equation, and then from the 3 points create 2 direction vectors, and then you're good from there. Okay, properties of planes, we've kind of covered all this, but this is more visual. You can see that if you had 2 planes that were perpendicular, that if you did the dot product between the 2 normals, you will get 0 because it's 90 degrees. And if you had 2 planes that were parallel, you can see that the normals would be scalar multiples of each other. Okay, last page. Okay, so these are just kind of miscellaneous questions. How do you get some information from the Cartesian equations? Okay, first one is we got these 2 planes, pi 1, pi 2, both given in Cartesian equation form. Show that these are perpendicular. Well, you know they're going to be perpendicular, just like we said from the last page. If we take the normals of these 2 planes, we can strip out the ABC values. So 2, negative 3, 1. Sorry, yeah, 2, negative 3, 1 for the first normal, and the second normal is 4, negative 3, negative 17. Okay, so if we do the dot product, we're trying to show they're perpendicular. So if we did the dot product, we should get 0. And if we don't, they're not. If we do get 0, they are perpendicular. If we don't get 0, they're not perpendicular. So N1 dot N2, that's just multiplying and adding them together. So that would be, sorry, I got the wrong number here. That should be a 4. So 2 times 4 is 8. Negative 3 times negative 3, positive 9. And 1 times negative 17, negative 17. That is equal to 0. Therefore, the 2 planes, pi 1 and pi 2, are perpendicular. And here's the short form for perpendicular. We want to save some time. Okay, so it's really just looking at the dot product of the normals to see if they're perpendicular. Now in this case, we've got two other planes, pi 3 and pi 4. We want to show that they're parallel but not coincident. So coincident means, well, coincident planes would be parallel, but coincident planes are basically the same plane. So you want to show that these two planes are parallel but not the same plane. Okay, so again, we can strip out this normal 3 has components 2, negative 3, 2, and normal 4 has components 2, negative 3, 2. Okay, so if we look at that, now these two are exactly the same. So we can say N3 does equal N4. Okay, so therefore the two planes, we definitely know they're parallel to each other. Okay. Now, so how do we tell that they're not coincident? Well, that's when we look at the d values. Okay, so here the d value is negative 1. Here the d value is negative 3. So d1 equals 1, d3 equals negative 3. So since d1's not equal to d3, sorry, hold on, that should be, let's call these 3 and 4, so d3 and d4 are different, but the planes are parallel, therefore the two planes pi 3 and pi 4 are not coincident. So they're parallel but not coincident. They would be coincident basically if one of these was a scalar multiple of the other, the whole equation. Okay, last question. This is a useful one. We haven't even really touched it, but this is that formula to get the angle between two planes. So we have pi 5 and pi 6 this time. We want to get the angle between them. So first thing we have to do, if you remember the formula, we need the normals of each of the planes. Normal 5, and that's from pi 5, so that has a normal of 1, 2, 3. Normal 6 from pi 6, that has 3, 2, 1. Okay, so if you remember the formula to get the angle, we call the angle theta like we always seem to do. Cos theta is equal to, so we've got n5 and n6. So the dot product of the two normals over the product of their magnitudes. Okay, so if we do the dot product, we get 3 plus 4 plus 3, so that's going to be 10. The magnitude of each of these, if you remember, you basically square each component and combine them, so that'd be 1 plus 4 plus 9, that's root 10, and 9 plus 4 plus 1, that's root 14, but we take the square root. Okay, and if we take the cosine inverse of this, we get we'll get an angle of 44.4 degrees. You could also do 180 minus that would be the paired angle, the obtuse version. Okay, so that's a variety of questions here, but basically either creating Cartesian equations of planes or starting with the Cartesian equation and converting it into vertex or parametric form, or finding the angles, finding out whether two planes are parallel or perpendicular. Okay, so that covers the last lesson from our Unit 3. We'll be doing one more lesson from Unit 4, and that's going to be finding the intersection between a line and a plane. So we'll be doing that next, and then we'll have an assignment based on all of Unit 3 plus that one lesson. Okay? Hope you have a good day.